All right, hello everybody, and welcome back to the Texas Financial Derivatives educational modules. Today, we will be introducing the Black-Scholes model, and for this semester, this should be our last video. We've certainly come a long way. We started out with talking about just basics of options and option strategies, continuously compounded rates, probability, expectation, variance. We went on to talk about simulating data with Monte Carlo. We talked about binomial trees and probabilities, expectations of stock prices, and now we're kind of trying to help tie in all these ideas together into one final model that helps us with obtaining the theoretical price or the theoretical premium of a call or put option, and it is called the Black-Scholes model. So first off, let's start with a recap, which is what we talked about in the last video. So in the last video we talked about conditional expectation of stock prices, where we were interested in, given our stock price has gone above or below some strike price K, where K can be any price, what is the expectation of that stock price? Given we know it's already past this boundary, what can we expect the stock price to be? And we found that ended up being equal to our initial stock price times e to the r minus delta t, which is our expectation, can be thought of as the expectation of the stock price at time t, times n of d1 divided by n of d2. For the expectation of the stock price given s of t, given the stock price is less than k, we found that to be equal to s initial e to the r minus delta t times n of negative d1 over n of, this should be negative d2. Yeah, negative d2 right here. Sorry about that. Where d1 is equal to ln of s over k plus r minus delta plus 1/2 sigma squared times t divided by sigma squared of t, and d2 is equal to d1 minus sigma squared of t. So after recapping what happened in our last video, now that we know the probability a stock price falls above or below some strike price K and the conditional expectation of our stock price within that region, let's use that info to derive the premium of a call and a put option. But before we do that, we need to make some assumptions about our model and how we're going to derive this price. Most of these assumptions are going to deal with knowing a lot of these variables mentioned up here and assuming they are constant as well. Because if we are going to build a model that you will see requires a future expectation of payoff, we need to know that the variables that are involved in that expectation and discounted expectation, we need to know what they are, as well as know that they are constant. And so let's go through some of these assumptions. So our first assumption is that the continuously compounded returns are our particular risk-free rate is known and normally distributed over time. Volatility is, this is more of our alpha. The risk-free rate is mentioned down here. But our continuously compounded returns, our alpha in the stock price accumulation is known and normally distributed over time. Volatility on the returns is known and constant. Future dividends, delta, are known and constant. The risk-free rate is known and constant, and we use the risk-free rate in our model. There are no taxes or transaction costs, which means there is a frictionless market. Short selling is allowed at no cost, and any investor can borrow or lend at the risk-free rate. So these are 7 assumptions we need in building our Black-Scholes model, which is used to calculate the premium of a call or put option, the theoretical premium of a call or put option. And most of these you can see are just simply saying that we know what our variables are, and we're assuming that they're constant too. Because if our variables are changing all the time, this can greatly affect what us when we discount our payoffs, as well as what our expected payoff might be. And so let's go to the next page. So when pricing an option, the intuitive approach that we want to have here is that when pricing an option, its premium, i.e. the value / price we pay at time 0 for the option. So whenever I go to someone and I say, hey, I would like to purchase a call option or put option, the price I pay for it at time 0 is the present value of our expected future payoff. So what we pay at time 0 is what we would based on the expected future payoff of that option based on how the stock moves up and down, discounted to the present. So that's what I mean by the present value or expected future payoff. So to begin, for a call premium, let's just start with the definition. The call premium, like we said, the premium of the option is equal to the present value of the expected future payoff. So present value, expected payoff. Well, the present value part is just us discounting the expected payoff to time 0 for when the payoff occurs at some time t, some expiry time t of our option contract. Well, that's just given by e to the negative rt. Our payoff for a call option is either 0 or s sub t minus k. We only attain a payoff when the stock price is above the strike price, and so it is just the max of these two. We won't incur a negative payoff. So this is equal to e to the negative rt. In one scenario, we get 0. So we could either get in this max function, we could either get 0 or s sub t minus k. So we have expected value 0. Well, we get a payoff of 0 when the probability of the stock price is less than the strike, less than or equal to the strike, or we get plus the expected value of the stock price minus k, and this should have given s sub t is greater than k in it, times the probability that event occurs. So this right here is pretty much saying, denoting this expectation is given the stock price is above the strike, what is our expected payoff from it? And so that's what this part means right here. Well, this just gives expected value of 0 is 0, so we can cross that out, and we get e to the negative rt times the expected value s sub t minus k, given s sub t is greater than k, times the probability s sub t is greater than k, which is equal to, just through linearity of the expectation, we can break this up, and we can get e to the negative rt times the expected value s sub t, given s sub t is greater than k, minus k, times the probability the stock price is greater than k. Well, we know what this is. We know our conditional expectation of the stock price, and we know the probability the stock price is greater than k. We did this 2 videos ago, and we did this in the last video. So plugging these in, we get e to the negative rt times s initial e to the r minus delta t times n of d1 over n of d2 minus k times n of d2, since n of d2 is the probability the stock price is greater than k. we distribute n of d2 in, and n of d2 times this n of d2 on the bottom, those cancel out, and then this n of d2 gets k, gives us minus k times n of d2, and then we distribute the e to the negative rt in as well, and we get s initial e to the negative delta, we get the call premium is equal to s initial e to the negative delta t times n of d1 minus k e to the negative rt times n of d2. Let's do the same thing for a put. So again, just starting with the intuitive definition of a premium, the put premium is equal to the present value of the expected payoff, which is equal to the present value component is e to the negative rt times the expected payoff, where the payoff is maximum of 0 and k minus s of t. Well, with the law of total expectation, in one situation we have 0, where 0 occurs when s of t is greater than or equal to k, plus the expected value of k minus s of t given s of t is less than k, times the probability that event occurs, which is the probability s of t is less than k, which is then equal to e to the negative rt, since and then expected value of 0 is just 0, so this goes away, e to the negative rt times probability s of t is less than k, times k, since we can pull this k out since the expectation is linear, and since k is a constant, it stays the same no matter what, so we can pull this out. Whereas s of t, that will depend on k, and so we get times k minus expected value, the stock price at time t, given the stock price at time t is less than k. Well, we know the probability s of t is less than k, and we know the conditional expectation of the stock price given given the stock price is less than k. This is equal to e to the negative rt times n of negative d2 times k minus s initial e to the r minus delta t times n of negative d1 over n of negative d2. Distribute the n of negative d2 in, and the n of negative d2 times k gives us k times n of negative d2, and then the n of negative d2 times this, where there's an n of negative d2 on the bottom as well, so these cancel out, and we get the put premium is equal to k e to the negative rt times n of negative d2 minus s initial e to the minus delta t times n of negative d1. These two equations are essentially the Black-Scholes model. The Black-Scholes model is used for calculating the theoretical premium of an option, whether it be a call or a put, based on the initial stock price, the dividend rate, the time, the strike price, the risk-free rate, and the volatility of the returns as well. So let's do an example just to show all this and how we might use it in a problem. So an example is calculate the premium of a 3-month call option with initial stock price of 70, a dividend rate of 0, a strike price of 75, a continuously compounded risk-free rate of 0.15, and a volatility of 0.3. Let's go ahead and write out all our variables, everything we know. T, our expiry time, is equal to 3 over 12, because it's 3 months out of the 12-month year, which is equal to 0.25. S initial, our initial stock price, we were given is 70. Delta, our dividend rate, is 0. The strike price, K, is equal to 75. The continuously compounded risk-free rate, R, is equal to 0.15. And then the volatility of the returns is 0.3. So recall just from above, we said the call premium was equal to S initial e to the negative delta t times n of d1 minus k e to the negative rt times n of d2. Let's just start plugging in stuff. That gives us 70 e to the minus 0 times 0.25, so we just get e to the 0, n of d1 minus 75 e to the negative 0.15 times 0.25 n of d2. So we need to find d1 and d2. d1, remember, is equal to ln s initial over k plus r minus delta plus 1/2 sigma squared times time divided by sigma square root t, which is equal to 70 over ln 70 over 75 plus 0.15 minus 0 plus 1/2 0.3 squared all times 0.25 divided by 0.3 square root of 0.25. This gives us negative 0.13495. Recall our shortcut method for d2 is equal to, where d2 is equal to d1 minus sigma square root of t. So thus we get d2 is equal to negative 0.13495 minus 0.3 square root of 0.25, which is equal to negative 0.28495. Thus, the call premium C is equal to 70. E to the 0 just gives me 1. So we just get 70 times 1, which is 70. 70 n of d1, which is n of negative 0.13495, minus 75 e to the negative 0.15 times 0.25 times n of d2, which is n of negative 0.28495. We look at a z-table and we find the probabilities. We find the left-hand side probabilities of these z-scores, and plug those in, and we get the call option premium. The price you will pay at time 0 to purchase this call option is equal to 3.2253, or pretty much $3.23. This is what the Black-Scholes model is used for. It is a model that calculates the theoretical price premiums of options, whether they be a call or a put, and this kind of ties in all the ideas we've been talking about. How we've talked about probability, how we've talked about expectation, how we talked about distributions and the binomial up and down movements of stocks, and how we calculate option values based off of that. And now we're putting it into a continuous approach, and just showing how we've started from option basics and option strategies and going all the way into figuring out how options are priced in the market as well. They are priced based off the present value of their expected future payoff. So thus, if the expected payoff of an option was very high, then it would be priced very high as well, because it would be very valuable. If you wanted to buy a call option and the market says that it's going to produce a big payoff, well, it's going to cost a lot to you as well. So anyway, this is all I had to say for this video. I hope y'all learned a lot. We've come a long way in just talking about all different kinds of scenarios and topics that are very common in actuarial science, and as well as stock market evaluation and just financial derivatives. And so yeah, this is all I had to talk about. I hope y'all learned a lot. Please remember to like, comment, subscribe to the video, and post any questions that you might have so Austin and I can get back to you. Well, thank you guys. I enjoyed teaching y'all, and I hope next semester we will have a lot more to discuss, and possibly introduce y'all to some other interesting concepts. Thank you. Bye-bye.